So there's no assistant here. But okay, today we're going to start chapter 6, similarity and matrix diagonalization. I have made some notes for you, and I mentioned to you. I have graded your participation of the last week with the grades in it, and also I have uploaded the lecture note on chapter 6. So you must have read it before you come to school and come to class today. So, and also, in addition to that lecture note, I have uploaded the Korean version of the lectures here. And also, if you go this website, then you will see the Korean version of the lecture note on matrix diagonalization. All you have to do is just go through on, like, for example, here, similarity and matrix diagonalization. If you go to section 2, then you have all the information that you can easily follow. So I believe you must have read it before you come to class. Okay, and also you will find the YouTube lectures by
6장
myself
5절 발표를 맡게
and
된
my student
권혁뜸이라고 합니다.
who have solved the
1번
problems
문제를
in the
설명해
section.
드리도록 하겠습니다. 선형변환 t는 yz평면에 정사형시켰.
Okay, and 자, 그다음 7장 4절 노말 매트릭스입니다. 행렬의 대각화에서 에센스가 되는 내용이에요. 이 앞에서 봤듯이 허미시안, 스키 허미시안, 유니타리 행렬은 모두 유니타리 다이고널라이저블이에요. 그런데 이런 행렬들이 아니면서도 유니타리 다이고널라이저블한 행렬이 존재하는 것을 아까 위에서 확인했단 말이에요. 그렇다면 그 갭을 채워줄 수 있는. So you won't have any difficulty after you read the lecture note that I have given to you, and then for the part that you have not understood fully, then you can go back to the Korean lecture note and as well as the lectures on each of those things. That also you will be able to find the related sections in YouTube. Where I have known to you. And also, I have given some information on the undergraduate research project for you, which was announced a couple of days ago. This information says you that you can apply for the undergraduate research for this amount of research fund, about 350만 원이면 about 30,000 and about 2,000 to 35,000 dollars for your own ideas and your undergraduate researches. So you may just go there to download the application form to take a look. Okay, and our RU lab will support your application and your research as well. And what else? And these are the problems that I have reorganized. So for the chapter 7, 8, and 9, I will try to assign you some of the problems that you can submit. About 10 problems for each will be given, and you will start to solve it, and you will get the finalized okay by myself to finish it before you submit it. And this is the last week's your performance on problems. Okay, what else? And today Oh, here. I can. Okay. Here you must remember you recall the name that I mentioned. La Bezier is the author of this linear algebra book, which is quite popular and also widely used in United States. Here, uh, here he will add his comment on the section similarity and diagonalization today with the functions that you never seen it before. Okay, here if you do it in Sage, then you will see all those notations changed as mathematical symbols like this, which is not done on Internet Explorer. And Professor Bezier have worked on this, and he have given lectures with this book in his university, as well as other schools. And you can also download this whole textbook in here. So we are thinking to use this book. You can just download this whole book in various versions, PDF version and text version as well, and with the size that you can choose. So usually you would like two-side printing A4 papers or one-side printing of this PDF file in A4 size papers. Okay. Anyway, you. And also in the Q&A sections, here is your online attendance up to today. I see most of you are working very hard to catch up the lectures and the information that I have offered, but there are a couple of students who just skipped a couple of weeks' work. Okay, and I will, before we start, I will explain what I have, the comment that I have made for you. Online attendance you looked it. And also, when you solve the problem and revised it and you think it is a final answer, then after you announce your solution is final, then you are welcome to come to my office to get the finalized okay by me. And Miss Jiun Kim solved the problem solved a line in the page 179, and she said she didn't understand this sentence. So I made the explanation, and I also made the file for that. So in the last line of page 176 in our textbook. So if in Rn, in a vector space Rn, and if you assume this inner product which was used is a dot product, then you know this can be written as this one. Then you will see this dot product and the product of this 1 by n vector and the n by 1 vector is a 1 by 1 scalar. With the information of this, you will see the projection of x, vector x here. This should be Rm bold x here. Rm bold x. Okay. Here, so the projection of the vector x on U can be written in this way from the lemma of 5.11. Then, as you see, this is the scalar which can be written as a U transpose x. This is
a product of scalar on a vector whose size is n by 1. Then this is, since this is a scalar, this can be written not only in front of the vector, so you can move it to the back of this vector. So still, this is a scalar multiplication of vector on a vector. So from here you can write this one in terms of u transpose x like this. Actually, that was what was meant in here. The question by Miss Kim was, why this projection of x on u can be written in this way is that's what it was meant. Jiun, Kim, she should understand. Now she must understand it. Okay, and what else? What else? Okay, and oh, okay, here. Okay, I have distributed the problems that I have given to you here. Here. That's the file of this one. Okay, these are the problems that you have solved and revised and finalized. I have graded it, and so these you're supposed to revise it before you get the permission to finalize it by me. So you just follow it and to finish the problems like this. Okay, so these are the problems that I have handed out to you. Okay, what else? What else? And also, also, Mr. Yoon asked, also I have uploaded some information on the companion matrix, which was appeared in chapter 6. And this, you may take a look the relationship between this polynomial and this matrix. So it has a very close relationship between it. The characteristic polynomial of this matrix is this one, and from this polynomial you can always make this type of matrix, which is called the companion matrix of this characteristic polynomial. So you can take a look on it too. And Mr. Yoon Woo-sung solved the problem 6.3 at the page 215, and I made the collection. So like this. You just find the matrix A and B such that determinants are same and traces are same, but they are not similar. So if you choose A matrix like this and B matrix as identity, then A and I's are not the same matrix, but their determinants and traces are same. But definitely, they are not similar. So if you assume they are similar, then there exists a non-singular matrix U. Here you need there is a non-singular matrix Q such that this means A should be an identity matrix, but you know A is not an identity matrix, so it occurs a contradiction. So if you choose a matrix A and B like this, then it satisfies the condition which was asked. So you can finalize it like that. And what else? And Mr. Yoon also asked the definition of the normal matrix. And normal matrix is not directly related to the normal vector. But this is a definition of a normal matrix. If a matrix satisfies this relationship, then it is called a normal matrix, which guarantee the matrix, the matrix A is diagonalizable if and only if. That's the condition for that's the if and only if condition for the matrix diagonalization. Matrix A is diagonalizable if and only if the matrix A is normal. like this. It satisfies this condition. Okay. And what else? And also, Mr. Yoon asked that if matrix two matrices are unitarily similar, then whether it is similar or not. Definitely, if two matrices are unitarily similar, then it is similar, because U star is unitary matrix U satisfies this condition, which means U star is a U inverse. So U star A U is equal to B means U inverse A U is equal to B. So they must be similar. Mr. Yoon, you understand that? Okay, good. And Mr. What? Mr. Song and Mr. Who asked it? Yeah. No. Yeah, you asked that whether the other way of finding this diagonalized the diagonal matrix which is similar to a given matrix, and the way that we are using is the best way. So yeah, you better use it at this level of study. And there are also the comments that I made for your questions here and there, and then you can take it. For the orthogonal projection, I mentioned this website that this actually this is the graph that I explained it on the board a week ago, that gives you the y, this projection of y onto the subspace WK can be written in this way. Actually, this figure explains all of those concepts. Okay, I think those are the things that I made a comment. So today I may start with the lectures on this matrix diagonalization. Yeah? Okay, you know the definition of eigenvalues and eigenvectors. And diagonalization problem is given like this. For a given square matrix A, find an invertible matrix Q such that Q inverse AQ is a diagonal matrix. If it does exist, and if it does not exist, then you find out what is the criteria that it can be diagonalized like this. Okay, so we first, in order to examine those diagonalization problem, we introduce eigenvalues and eigenvectors, and there are several applications of matrix diagonalization. Okay, these are the application of this matrix diagonalization technique. It has a wide area of application of matrix diagonalization. Okay, you know the definition of eigenvalue and eigenvectors like this. So if it satisfies, if we call the non-zero vector x is an eigenvector of matrix A if there exists a scalar lambda such that AX is equal to lambda x. And also we call this scalar x is we call this lambda is an eigenvalue of A corresponding to the eigenvector x. Okay. And in geometrically, this means x and AX is parallel for the eigenvector x. And also, since this is a linear system of equation, if you move this one to the left, so let's just make A minus lambda I is equal to x equals 0, then it's a homogeneous system of linear equation. So you can find the solution set which forms a null space of this. We call this null space is the eigenspace of A corresponding to the eigenvalue lambda. So eigenvector is one of the vector in this subspace. Yeah, we know this is called the characteristic equation, and these are the properties of eigenvalue. If eigenvalue lambda is an eigenvalue of A, then it satisfies this polynomial, this characteristic polynomial. And also lambda I minus A is a singular matrix, and this homogeneous system has a non-trivial solution. And there are some examples that you have seen already, and you know how to find it. And the problem is this: the matrix having a repeated eigenvalue with insufficient eigenvectors. Suppose you have the matrix like this, then you know this matrix has the eigenvalue 2, whose algebraic multiplicity is 5. But if you solve this linear system of equation, ax is equal to 2x, then you will find only one linear independent vectors in the null space of 2i minus a. So in that case, you only have one linear independent eigenvectors. So, and for the complex case, you have. So there are some matrix that of size n that you can find the n linear independent eigenvectors, and there are some matrix that you cannot find the n linear independent eigenvectors. You saw the examples. So here's the lemma that if A is a triangular, then diagonal entries are exactly the eigenvalues of A. Yeah, you can easily show it because it satisfies this polynomial, which means this the A11 and ANs are the solution of this characteristic polynomial, which means this AIs and A2 to A11, A2 to ANs are the solution of this characteristic polynomial, which means those diagonal entries of A are the eigenvalues of the matrix A, of the triangular matrix A. If A and B's are square matrices similar to each other, then they have the same characteristic polynomials. Okay? Okay, it can be shown. If it's similar, then you can easily show the characteristic polynomial of these two are exactly same, since this Q and Q inverse can be vectored by the multiplicative property of the determinant, which was shown by Arthur Cayley. Okay, and easily you can show determinant of A is the product of eigenvalues, and trace of A is the summation of the eigenvalues. Why this is true? Who can tell me the reason? Here, the same thing. On the other hand, here, find the determinant of lambda I minus A is like this. Yeah, since this comes from the definition of determinant, the eigenvalues. So let's say determinant of these are same as this. Then see, just compare the coefficient of lambda n minus 1 in two ways by expanding both sides. Then on the left-hand side, you will see the coefficient of lambda n minus 1 is the addition of lambda i's. Coefficient of lambda n minus 1 in the right-hand side is this, which is a trace of A. So trace of A is same as the addition of the eigenvalues. This can be easily found by comparing two polynomials and the coefficient of the lambda to the n minus 1. Okay, all this comes to the properties of the similarity ideas. We haven't explained the similarity yet in this course, but you have learned those concepts from the introductory linear algebra class. Okay, so here you see the determinant and trace of A are invariant under similarity. That's why the J.J. Sylvester, who defined the matrix terminology, is the specialist and most popular in the invariant theory, which is still a major research problem in the 21st century. Invariant subspace problems was a major research area of J.J. Sylvester, who defined the matrix and initiated the early researches on the theory of matrices. Okay, here is the corollaries. Invertible, since invertible, if 0 is not an eigenvalue of A, because determinant of matrix A is the product of lambda i's. If one of the eigenvalues are 0, then definitely the product of the eigenvalue should be 0, which implies the matrix is singular. Okay, so if it's not a singular, then none of lambda i's can be 0. Semi-rim, understand? Understand that? Okay. And for corollary, for any n by n matrix A and B, following are equivalent. 0 is an eigenvalue of AB, and A of B is singular, and 0 is an eigenvalue of BA. These are also, so from here, from this observation, you can find the AB and BA has the same eigenvalues. It's a very interesting thing. But if this corollary is working for the n by n square matrix, what if this matrix AB has a different size? What will be the conclusion that you can expect? Okay, so for the different size of matrices, if the product is defined, they have the same eigenvalues with the 0 eigenvalues for the redundancy of the sizes. Yeah, here is the proof of the theorem for the above, and there are problems. All those problems were solutions were given in here. So you can take a look here. I made all typed up, so you can take a look on those problems that I mentioned here. Here is the full detail of the solutions, so you can go through it for what you are curious. And there are some problems which was not fully solved here, and that will be your homework to do. Okay, that's what I asked you. There are some problems which is not fully solved, or the problems that was not finalized okay by me, then that's the problem that you just have to finish up. Okay? Okay, next. Here is the diagonalization of a matrix and similarity concept. Here, I invited Professor Robert Beezer to explain you in his way of teaching on it. Laugh? Would you help me to finish up this chapter? Okay, great. Thank you. Yeah, please. Here, as I mentioned, here, notice I uploaded this website, which already I made it up here. So he will explain the similarity and diagonalization, which was the last part of it. After that, the other sections are is applications of the matrix diagonalization, which was was added. So on those parts, I know some of you are doing your project. So yeah, that you will explain by yourselves. But in here, for the similarity and diagonalization, Professor Robert Beezer, and who is the author of this popular book of linear algebra, will explain it. Okay? Yeah, so you can go through it, and when you need, you can stop it, and you can pause it, and you can continue.
Okay, great.
Yeah, we welcome Professor Beezer.
So feel free to go to the book on your phone or whatever you like if you want to follow along. It'll be the same thing that is up there. So I'll show you a few things in the book and how it works, and I'll try and concentrate on the SAGE material, and I'll do the one proof that I was asked to do. We'll do carefully. So there's the definition of similar matrices. If you take an algebra course later, like abstract algebra, maybe a discrete mathematics course, equivalence relations will show up, and that is discussed right here. So similarity is an example of an equivalence relation. Equivalence relations are like a loose version of being equals. So an object should be related to itself. If in the case of a similarity, if A is similar to B, then B is similar to A. And then there's transitivity. So if A is similar to B and B is similar to C, then A will be similar to C. So that's an example of a general thing called an equivalence relation. And you might see that in other courses. So this might be your first example of that. There are lots of places you can click on things in the book. The proofs are always sort of hidden away. There's the same proof that Professor Lee just showed you. There's more detail. This is a first course, so my students are straight out of calculus, and they're not very good at proofs yet. So I do every single step if you want to go back and look at things. These are all various facts from other parts of the book. So, for example, a key step in this proof is where you push the determinant into that product and break it up into a product of determinants. So there's a theorem that has a title, Determinants Respect Matrix Multiplication. And down here you'll find a link for that proof. So if you don't remember what that theorem is about, or if you don't remember its proof, you can just keep clicking on various links there and opening things up. And they're easy to put away. So we'll put that away as well. So you've seen the definition of a diagonal matrix being diagonalizable. The book has a whole collection of what I call archetypes. So there's about 24 examples of systems of equations, matrices, and linear transformations. And in those examples, I try and compute everything I can for them. So there's an archetype B. Which one is to open a new tab, Sengu? Which one will be a new tab?
So this is left, right side here.
Yeah, I did left, but I don't know which it is.
Oh, so you wanna
I'm gonna
open up the new one?
A new tab.
Ah. Okay, then just not by clicking.
Okay, I can do that.
Okay, yeah, I think it doesn't work in here. Yeah. It's
Yeah,
not.
okay.
It's not connected to new tab. So.
Okay.
So you just open it.
All right. Okay. All right. So this matrix B here, I've done the diagonalization on B, and this is just an early example. So we're still just talking about similarity. Archetype B begins as a system of equations. But there is a complete description of that system of equations. It's reduced row echelon form, solutions, pivot columns, column space, row space, inverse, dimensions of various subspaces. There are the eigenvalues and eigenspaces. There's finally the diagonalization down at the very end. So there's a whole collection of examples. They're all listed here on the side. That's how you can get to all those. So we'll go back to where we were in similarity and diagonalization. I should show you. Throughout the book, there are about 100 examples of how to use SAGE. So when we're talking about similar matrices, there's, yeah, there it is. Okay. So there's some description of how to use SAGE. I've been experimenting with getting fonts from Google, so that the monospace font's a little weird. It goes with space after. This is a place that's from what's called the SAGE single cell server. You can type any SAGE code in here you like and just run evaluate. And what I've done in the book is have sections where there's examples already in it. So there are a couple of big matrices, and the command down there is similar. We'll check that for you. If the matrices turn out to be similar, and you want to find the matrix, I call it S. I think Professor Lee might have been calling it Q. If you want to find the matrix that you use, the invertible matrix, it will return that for you as well. All I'm asking here for is whether that's true or false. Okay. So that block of SAGE code went to a server at the University of Washington in Seattle, was evaluated, and then the results, in this case just true, came back. What am I doing here? The transformation matrix is exact, and you end up with some lot of complex numbers that are kind of messy. It was a little bit easier to print the transformation matrix out numerically in this example. This is a matrix that is not similar to one of the matrices that we had before. And if you want to try something, if you want to do something, we'll do something exciting. You know the answer to that, right? But you can do whatever you want. So any Sage code you know, and you can cut and paste from those examples up above. And there's always a little practice area down there at the bottom. So you might know the Sage notebook, and that's a good place to save your work and build up commands. But if you just want to do simple things.
The eigenvalues and eigenvectors of this matrix here. Or just you can add the line here. Eigenvalues and eigenvectors.
I think it will know. Let's see if it remembers what C is first. Yeah, okay, good.
We can do computation with the help of tools without installing any software.
So you can put your eigenvector on the right of your matrix, or you can put your eigenvector on the left of your matrix, depending on how you want to do things. Now it doesn't know C.
You can continue.
It's lost something.
Yeah, they will practice it because they will be able to find the Sage command of others. Practice.
Okay, so this is the theorem that Professor David talked about. Square matrix, diagonalizable. It's an equivalence if and only if you have as many linearly independent eigenvectors in of them as your size. So if you can find a basis for each eigenspace, then you can generally take all those bases for each eigenspace and put them together. And if you have n vectors in total, then you are able to diagonalize. The proof is constructive. So this I think is the interesting path. Assume that you've got eigenvectors and see if you can diagonalize. Like I said, the proof is constructive. So this is the matrix you want to build. So if you actually want to do a diagonalization, you want to take your eigenvectors and make them the columns of a matrix. So I'm calling it R here. I'm using a different letter than S because I don't want to make it look like I already know that they're similar. And there's the diagonal matrix, and those are your eigenvalues down the diagonal. So I like to do my proofs this way. I start with something and I end up with something else. So R is just all the eigenvectors in a matrix. How do you define matrix multiplication? You do a row out of a column?
Row column.
Yeah, okay. Right. So most people will define the product of two matrices by taking a row of one matrix and sort of effectively tilting it up and doing a dot product or a product with another column. And then that's a single entry of your product. Okay. So the way I have set up the book.
You understand what he means. And we call it the King Sejong's rule here and here. IJ's entry.
Yeah.
We call it it's like this. So this is the first character of Korean character. This is the first character which was invented by King Sejong. So we call it the King Sejong's rule on matrix multiplication.
Do you think that will work at home for you? So I have a different definition. So I try and do linear combinations really early in my course. And I've got systems of equations, but I don't have matrix multiplication. So I can't write a system as A times X equals B. So when I system, I just have A and I have B, and that's the notation that puts them together. But it's a long time in my book until you get AX equals B. So I do linear combinations for a long time. So I'm going to show you my definition of matrix. So you can see the first thing I'm going to do here is use my definition of matrix multiplication. So this is my definition of matrix multiplication. There's nothing wrong with it. It's just a choice. You know definitions are if and only ifs, right? We never write them that way, but we say some word if and only if. So if you have a lot of things that you know are equivalent, if you have a lot of things that are if and only if, you can sometimes use a different definition than somebody else, and then their definition becomes your theorem. Your theorem becomes their definition. So this is how I define matrix multiplication. You're going to multiply A and B. B has a bunch of columns. And then A is going to multiply each column separately. A matrix times a column is again a column, right? You think about your size. How do I define a matrix times a column? So a matrix times a column is the scalars in the column doing a linear combination of the columns of the matrix. So I have lots of linear combinations, and then I say, well, this is really useful. A matrix times a column vector is just a linear combination of columns. So I call that the matrix vector product. That has a definition. And then matrix multiplication is just a lot of matrix vector products. Right? And that's what, no matter what you use as a theorem, that's a good way to think about matrix multiplication, especially a matrix vector product. So a matrix times a vector is the entries of the vector doing a linear combination of the columns of the matrix. A lot of proofs get easier if you think about it that way. And what I do is I get King Sejong rule, I get that as a theorem. So I have to prove that. I have to start from this definition and then somehow get the sum of the AIKJs. I have to get that as a result of my definition. And it's pretty easy to do. Okay? So that's what's happening. Let's go back to this proof. That's what's nice right here. So the A times this matrix of eigenvectors, I just get to put the A in front of each eigenvector. And what's a matrix times its eigenvector? It's just its eigenvalue times the eigenvector. Things are really getting simple fast. E's. So what are the E's? The E's are, I call them the standard unit vectors. They're the nicest bases you can think of. All zeros and a single one in strategic locations. Also the columns of the identity matrix. So now what happens? If I take my diagonal matrix and I multiply it times the vector that goes 1, 0, 0, 0, 0. Well, think about, again, the matrix vector product. The matrix times the column vector. That's just the 1 times the first column. And then 0 times all the other columns. So all I'm going to get is the first column. The matrix of eigenvectors times E2. It's just going to pick out the second column. That's the second eigenvector. All the way along. So this is kind of backwards. You would think of explaining it this way. But they're still equal. Now it's really easy. I just push my scalar in the eigenvalue. We can do that kind of associativity with matrix multiplication. And then I can actually pull the R out. That's my definition of matrix multiplication again. And then the R inverse that I'm using for the similarity, they cancel each other out. And what's left? Lambda times E1, lambda 1 times E1, that's a lambda 1 in the upper corner. Lambda 2 times E2, second column, second row. Lambda 3 times E3 is third column, third row. That's my diagonal matrix. Okay. Other questions about that? So I think that's a good example of, you've got a different definition and it's just fine. But that's a good example of how thinking about matrix multiplication differently sometimes makes a lot of proofs go smoothly. Let's see. Okay, so the other half of the proof is sort of the same ideas. I think if you understand that half, you can understand the other half quite easily. So let's find some sage stuff. So this is a similar theorem. What did you call it when you don't have enough eigenvectors? When your eigenvectors are as big as your up there, then it goes.
Sometimes it's non-deficiency.
So sometimes called it vectors. So when can you diagonalize a matrix? There are various theorems about that. One of them is you need to have as many eigenvectors. In other words, the dimension of the eigenspace has to be equal to the algebraic multiplicity. So the number of times your eigenvalue shows up as a root of the characteristic polynomial. So in my notation, gamma is the geometric multiplicity, G. And so that's the dimension of the eigenspace. Alpha for A, algebraic multiplicity, that's the number of times the eigenvalue shows up as a root of the characteristic polynomial. If these are equal, then you can always do the diagonalization. And if they are ever not equal, you can't do the diagonalization. Okay, so it's if and only. So that's a really nice characterization. And I mention that because I'm going to show you how you can see that in Sage. So here's the Sage routine on matrix diagonalization. Okay. So
그러면 이쪽은 기한 S적 중복도 알지만 멀티플리티 오는데 지오메트릭 멀티플리티 아이겐스페이스 디멘전 1이잖아. 그러면 대략 불가능한 거죠. 그러면 여기 1차 독립의 아이겐베크가 5개가 있으면 그러면 아이겐스페이스 디멘전이 다섯 도착할 수 있지. 그러면 기하적 중복도 오고 코레스폰딩 아이겐베크 2가 꼭 5라는 소리잖아. 그러면 대적 중복과 기하적 중복과 5개는 대략 가능한 거죠. 그런 그 노테이션만 쓴 거예요. 1차 독립의 아이겐베크가 5개 존재한다는 게 기하적 중복과 5.
So here's a good size matrix. So we saw this command just a minute ago, eigenmatrix right. Eigenmatrix right gives you two things. I'm sorry, we saw eigenspaces. This is eigenmatrix right. It'll give you two matrices back. So this looks a little bit strange, but you can do this in Python. I can capture the diagonal matrix that'll give me back, and I can capture the matrix of eigenvectors. Okay? So, and all I'm going to print from this first one is just the D matrix. Okay? So that's always going to be your n by n matrix. It's always going to have your eigenvalues down the diagonal. It's always going to have them repeated. So we can see 2 is showing up twice as in -1, -3. Zeros and eigenvalues up there in the upper left-hand corner. Right? The second thing that came back was this matrix S. That's a matrix of eigenvectors. Okay. I'll keep this down here. 0 is an eigenvalue. It has dimension. It has just algebraic multiplicity 1. The biggest its eigenspace can be is dimension 1. That is the basis vector for the eigenspace of 0. 2 shows up twice. Its geometric multiplicity cannot be bigger than 2. These two vectors are going to be a basis for the eigenspace of 2. So there's what you expect the diagonalization to be. This is equality. That's true or false. Right? 1 equals is assign a variable. 2 equals is to test equality. So that, we expect that to be true from the theorem. So is diagonalizable is a nice command, but you don't learn very much. Okay. So this is the interesting example now. So I'm going to do the same thing. Matrix, eigenmatrix right. I'll get a diagonal matrix and I'll get this S matrix. So there are the eigenvalues, -2 and 6, each showing up several times. But now I'm going to create S. Okay. So -2 is showing up 3 times. First 3 columns are a basis for the eigenspace of -2. Now you know what I just said is wrong. It's not a basis. The zero vector is never a basis, right? I like to tell my students the zero vector is death to a linearly independent set. Anytime you put the zero vector in a linearly independent set, you're no longer linearly independent. So this is what Sage does. Because there's 3 eigenvalues and you want to keep everything lined up, it puts in the zero vectors just to keep everything organized. So we've got algebraic multiplicity 3, geometric multiplicity 1. We're not diagonalized. Okay? Now, it happens down here as well. But the minute we know that we've got the 3 eigenvectors and some zero vector in there from Sage, we know that the matrix is not diagonalized. Okay? Now, what's kind of nice, though, is that D and S still satisfy a certain condition. So you would write similarity by taking the S matrix and moving it over here as S inverse. And my S is obviously not invertible. Okay. But the original matrix and the matrix of eigenvectors is equal to the matrix of eigenvectors times the diagonal matrix of eigenvalues. Even if you put a 0 column vector in there, like Sage does, that relationship will still be true. And you can check diagonalizable, and that's false. This, okay. I'll real quickly, Sangu, show the, I've got an orthonormal diagonalization section. I'll just point it out to it, because I won't talk about it long. So this is the very last section of the book. There's lots of other material, and I've reorganized it in sort of the second book. But I've just noticed in the discussion earlier, you're talking about unitary matrices, normal matrices, what I call orthonormal diagonalization. Some people call it assured decomposition. There's different names for these things. So if you are doing your work with triangular, upper triangular matrix.
Complex case, because the unit type is diagonal. So this is a real matrix.
Yeah, so I do everything. The whole book is over the complex numbers. So you might talk about Rn. I always talk about Cn. Because when I get to eigenvalues, if you do things in Rn, you start with the matrix of reals, and maybe you have an eigenvector or something with real numbers, but then you have a complex eigenvalue. What do? You multiply the complex eigenvalue times your matrix or your column vector full of real numbers. You've left your number system just to accommodate the complex numbers. So I just put all the complex numbers in at the beginning. When I get to eigenvalues, I don't have to talk about complex roots as some kind of a special thing. It makes things easier too, because every polynomial that you can build with real coefficients factors into linear factors over the complex numbers. If you do things over the reals, you know you have a problem. You only get down to quadratics, right? And if you look at this kind of orthonormal diagonalization, when it's done super carefully over the reals, instead of getting a diagonal matrix, you get little 2x2 blocks that correspond to the quadratic factors.
So in your school, you deal with the complex matrices from the beginning?
Yes.
Everything.
Yeah, well, so I like to joke with my students, if you look at the examples here, so you guys know a matrix whose determinant is 1. The determinant determines 1, that means it's non-zero, so it's invertible. You might know this formula for the inverse, where you take the matrix of minors, the n minus 1 by n minus 1 submatrices, you take your determinant, and I think you transpose it, and you put 1 over the determinant. There's a formula to get the inverse of the matrix that way. And the only way you can introduce a fraction in that is there's a 1 over the determinant out front. So matrices with determinant 1 are really nice because you can prove that they're inverses. So if you start with a matrix full of integers, determinant 1, then its inverse only has integers, right?
One important part of this research study is similarity 구했어. S inverse AS equal D를 구했어. 그래도 그 관계를 완성시키려면 S inverse가 필요해. S inverse 구하는 게 class of work잖아. S 역행률 구하는 게. 그런데 S inverse가 S transpose하고 똑같다고 하면 그러면 얘기가 달라지지. 그러면 계산할 필요가 없지. 그러면 프린트만 하면 되는 거지. 그런 특별한 대각화가 있으면 모든 계산이 다 간단해지는 거예요. A 대신에 D를 갖고 생각하면 되고, 연결시키는 것은 그냥 S만 구하면 아이겐벡터입니다. 그럼 트랜스포즈를 갖고 S 인버스를 구하니까 계산이 아무것도 할 게 없지. 아이겐벡터만 구하면 모든 계산은 다 그냥 풀이지. 비용이 하나도 들지 않지. 그러니까 시뮬러리티를 한 다음에, 대각화를 한 다음에, 그 다음에 유니테이트를 하는 거죠. 그렇게 하면 계산이 아이겐벡터만 하면 모든 문제를 다 단순화시킬 수 있어요. 계산은 그냥 아무것도 필요 없어.
So this is some, I've written a lot of material. Some of the things I've been showing you, like, is diagonalizable or functions I've written for stage. This is something a summer research student did, so I saw your honors research challenge. So I did projects like that with my students. And I had one do this random matrix. So this is going to be rational entries, but they'll actually be integers. It should be a 6 by 6. Then I'm asking for unimodular. So that's determinant 1. That's a code word for determinant 1. And if this works, I'll show you the matrix, and then I'll show you its inverse. Okay? So there's a kind of nice matrix full of integers, and you wouldn't expect its inverse to look like that. But because it has determinant 1, it does. So you can take lots of, this is how I build exam problems and exercises for the book. I take like the answer, like the reduced row echelon form that I want. And then I multiply it by a unimodular matrix out front. And then that hides the reduced row echelon form. And whatever you have to do, whatever operations you have to do, often the fact that the matrix I use has determinant 1 and has a nice inverse means that the computations come out very nice and simple. So this is all getting to the question, do I do my matrices over the complex numbers? Do I do my matrices over the real numbers? The joke is I do them over the integers. You know you have to divide them. You can't always do things over the integers. So just to show you, so there's normal matrices that you were talking about. And here's how I phrase orthonormal diagonalization. So you take any square matrix, you can get a unitary U and a diagonal matrix D. If that happens, so there's your unitary diagonalization. That happens if and only if you are a normal matrix. And the proof, I'm not going to go through the proof, but the proof is kind of long and complicated. Lots of stuff going on. So that's a good one. Good one to read if you like. Is that good on time?
Thank you. Thank you very much.
All right.
Thank you for Professor. Wonderful explanation on the matrix diagonalization and the concept of similarity. And also, yeah, on here, I can, here, lab, okay, yeah, here, text 편집, okay, here, PDF 도구, 주석 달기가 아니라 기본, 기본 그리기 마커, pen. Here, since this is a tablet monitor, so I can write the proof here and examples and so I don't have to go there. And so it's still I can keep my voice on recording. There is a this microphone, this speaker, the wireless speaker here. So still we can keep things it, and also that the camera follows me by on this, so it's come and go. Since yeah, even though I don't have, even though we still have a half of the whiteboard here, but actually most of our activities can be done in this campus environment with this lecture table by itself. So that really helps us since 2003. So it's been about 10 years since we designed this learning environment at Sangkyungan University. I think, we have covered pretty much of the chapter 6, and other parts are applications. As you see here, at the end, you will see the the linear difference equation, which is application of matrix diagonalization, and also for the linear differential equation, and these are your reading part, and some of you will challenge on these matrix functions, etc. But this is not a requirement for this course, so it's a kind of your choice to go through the applications of matrix diagonalization. Okay, but also you can find the informations that I have uploaded on the web on this sections of your choice that you can help when you're doing your project. Okay, is there any questions so far on chapter 6? Okay, thank you.